All right, problem 109 from chapter 14. It's one of the review problems, right? We're gonna try to get through this in the next. This will definitely be the last one for today, right? All right, so I've got a mass C, which has a mass of 4 kilograms that is suspended from a cord attached to a minecart, which we're calling A, that has a mass of 5 kilograms and can roll freely on a frictionless horizontal track. A 60-gram bullet is fired with a speed V naught equal to 500 meters per second and gets lodged in block C. We want to determine A, the velocity of C as it reaches maximum elevation, and B, the maximum vertical distance h through which C will rise. All right, so, okay, let's draw. Let's draw a picture. I've got my minecart. We did a minecart pendulum before, right? But it was completely symbolic. This one's going to be slightly different, right? So here's my minecart and the block, right? And luckily this time, they didn't use B because I'm going to use that for the bullet. Right? We'll call this B. That makes sense, right? Because that's the bullet. And the bullet is fired at 20 degrees, right? And it's going to lodge itself in here, right? But we'll get to that part in a second when we do our momentum impulse diagram, right? Because this is going to chain. All right, so what kind of problem is this, right? Obviously there's a collision, it's a momentum impulse problem, but this is going to move too, right? And so we want to figure out this height. Well, can we get height from momentum and impulse? No, we can't. We need to use work energy to get height, right? And now if we remember from class, what's going to happen is this is going to get lodged in here, and then this will start to swing, right? This starts at rest. As this starts to swing, the minecart will start to move along the track, right? This will eventually reach a height, right? And normally, if this was a normal pendulum, we would say that at that height, our velocity is 0. But because it's attached to a minecart, it's moving at the speed of the minecart horizontally, and then it will start to swing back, right? And then you get some very interesting dynamic effects from it, right? So let's draw our momentum impulse diagram for our block C. Right? So in the beginning, right, I've got my block, and my block isn't moving, but this is mv naught, and it's at 20 degrees, right? And that means we're just going to end up with components of it, right? Plus my impulses. Well, what are my impulses? When these two things collide, they're going to have equal and opposite impulses, right? They're going to have equal and opposite impulses from the collision. However, we're still going to have our tension here, right? And as is typical, we're going to neglect the effect of weight as an impulse, right? That's our typical thing. Why? Because compared to the tension impulse, it's negligible. Right, we also know that the block is 2 kilograms, or I'm sorry, the block is 4 kilograms with a bullet of 60 grams in it. That's not going to be that big of a deal, right? And then at the final state, where we want to calculate this, right, we have the bullet inside the block. And this has a total, I'm going to call it mass total for the mass of the block and the mass of the bullet, times V, let's call it V prime, or just call it V prime. Okay. So really, when we're looking at this, yes, we have information about what's happening in the Y direction, but when we think about how this is going to move, right, at the initial state, right, so let's draw a state diagram too, because that'll be fun. And so at its initial state, we've got the minecart like this with the mass hanging off it, right? Call this state 1. And state 2, this now has some velocity, which is the same as this velocity, because this is the maximum height, right? So at state 2, if we use this as the datum, and I've drawn this not great, but we'll redraw it here, right? There's some height here, and we'll call it h, right? That's state 2. The potential energy of the cart hasn't changed. The only thing that's changed is the kinetic energy here and the potential energy of the block, right? Okay, so what are we gonna do? Well, if we look here, right, we take, remember, our impulse momentum equation is sum of my momentum for each particle plus the sum of my impulses is equal to the sum of my final momentum for each, right? Call these prime, right? Right, so each particle. Now at the end we only have one particle that we're dealing with, right? But this is our way of figuring out what V prime is, and then we're going to take that into our energy, right? Because we know at this state both of these have to have the same velocity. And the added benefit is we know at this point we only care about V prime. So I don't need to solve any of my y direction equations for my momentum, right? I can solve just my x direction equations. And just my x direction equations are what? Well, it's going to be mass of the bullet times V naught times, that's cosine of 20 degrees, right? Plus 0 is equal to the mass of the bullet plus the mass of C times V prime. I know everything there except for V prime, right? I can plug in everything there. So the mass of the bullet was 60 grams, which is 0.06 kilograms, right? So we got 0.06 times V naught, which I didn't write down, but was given as 500 meters per second. Right. 500 times cosine 20 degrees, which is going to be equal to, well, this was 0.06 plus 4 kilograms times V prime. So we can solve this for V prime, right? Solve this for V prime. And we should get 6.9-ish meters per second, right? That's what it should come out to. 6.943. 6.9435 meters per second. Because we can obviously measure it with that much precision very easily just by eyeballing it. Okay, so that's what V prime is, right? So that's the first part, right? Now we come down to our state diagram here, right? Now I have to analyze my energy, right? Because I'm told what? I was told specifically about this, that it's a frictionless track, right? I was told specifically that it's a frictionless track. So you could use work and energy here, right? You could. Alright. 1 second. Am I simplifying this too much? Maybe. See, I assumed that V prime, you can't assume that V prime is the final velocity of the cart, actually. Okay, let's continue. Let's just continue. There's a little bit more to this that we have to do. Now consider this, right? If we looked at just the mass of the minecart, right, by itself. Okay, so we can draw impulse momentum diagram for that as well. I'm going to get rid of this for a second. I need the room. Right. So we'll call this V prime for C. V prime C is equal to 6.9 meters per second. Okay. Alright, so going to get a new diagram here. My new diagram. Just for my cart, right? So I've got my cart, and the cart initially is not moving, right? It starts from rest. My impulses, in this case, I've got tension, delta T. Well, this should be pointed this way, right? Tension, delta T. And I've got the weight of the cart, delta T. Not going to ignore it on this one because it's being balanced. And this is going to equal MA VA prime. So what was V prime? That first one that we found, right? That was the initial velocity right after impact. I went too far ahead. I jumped into the future, right? So what we actually broke this down. First things first. We found the velocity right after impact of the bullet into the block. Now we need to figure out, right? And in this case, we'll have the same thing here. And this is actually the normal force touching the track. Because why? Because this is mass C, this is mass A. Right? So this is going to have some x direction velocity component here. Right? So this has mb plus mc times v prime c. Right? That's my momentum starting here. All right. So now everybody. Let me reiterate this, right? We started with finding the initial velocity after impact of the bullet into the block. The next part of this is now that the bullet is in the block, this now has some momentum for the block is going to start the motion, right? And this motion is going to start, and this is at the same time point, this is not moving, right? The impulse is here. Now, we have to take into account the weight of BC delta T, right? There is also tension delta T and tension and tension delta T right over here. We're just going to take everything into account. And what does this give us? This is going to give us, we'll call this mass BC times VBC in the x, and mass BC, VBC in the y. Right? So this will start to swing, right? So now we're saying that this is going to start swinging. So after impact, this will now have a new momentum where it starts to swing. And again, what are we going to do? We're going to sum our momentum and our impulse, right? So if we take just the horizontal components again, for mass BC, right? So we take the horizontal components of everything that's happening here. Okay, the horizontal components. What do we start with? Well, we get MB plus MC V prime C, which we know. That's equal to 0 plus 0 is equal to MA VA prime plus MBC VBC. The x direction. I've got two unknowns, right? I can solve for VA in terms of this velocity here. And so if I rewrite this, all right, because why would I want that? We'll see in a second, because when I use work and energy as my next, let's use conservation of energy, I'll have everything in terms of VA, and we can solve for VC, in the x direction, right? So it'll work out for me in the end. Right? So VA is going to be equal to 5.6, right? Because I'm going to plug in some numbers here too, for the sake of time, since we're almost up here. Minus 0.81 VA. 5.6 minus 0.81 VBC. Okay, so I plug in my numbers, I solve for V prime A. How do you know to do that? It doesn't matter which one you solve for, right? It doesn't, because you're going to end up with two equations and two unknowns, right? Now we're asked to find the height in this problem, which we will get, but you're going to have to solve for, you're going to have to use the constraint that we already knew, right? At maximum height, right? We talked about this when I drew the minecart, right? At maximum height in our state diagram, the velocity of A is going to be equal to the velocity of BC, right? Yeah. So let's keep this in mind, right? At the initial state, we're hanging here, and at some time later, we end up in state 2. This has occurred, and my pendulum flips up, right? And if I measure this, there's my height difference, right? But these two things now have what I'm going to call VA prime, right? At that time, right? Because when the pendulum swings up, eventually it will stop to change directions, right? And that's what we call maximum height, right? But at maximum height, the entire system is moving with the same velocity forward, okay? So if we are at maximum height, which is what we want to solve for, at max height, we know that VA is equal to VBC, right? So at maximum height, we plug in VA for VBCX, right? So I should write X. And we can solve that. We can get V prime A. V prime A is equal to 3.1 meters per second. Okay. Everybody with me so far? We good? We good?
You just plugged in VA prime for that.
So we're saying, you know what? We're only interested in this at state 2 when the height of the pendulum is maximum. And because the height is maximum, we know that the x direction velocity here has to be the same as the x direction velocity of the minecart. And so we're just plugging in VA prime for this and then solving. All right, so you end up with 1 minus 0.81, which is 0.19. So 5.6 divided by 0.19, right? No, that's not. I didn't do that math. You have to add it. It's 1.81. There you go. Now we're good. Now Dr. D can do addition and subtraction. Really, I'm really bringing home the confidence, I can tell. Okay, so now we have VA, right? It's 3.1 meters per second. So I'll throw that up on the top, right? Because that's the important number that we need. Why is that the important number that we need? Because we did this problem in class when we weren't shooting a gun at the thing, we were just hitting it, right? And we did the general solution for this. So now, this is when we need to use kinetic energy. Or, sorry, principle of work energy, but in this case it's conservation of energy, right? Because we're told that it's frictionless, so there's no non-conservative forces in our system. Alright, so work and energy, right? So this tells us what? The kinetic energy at some state plus the potential energy at that state has to be equal to the kinetic energy in the final state or another state of interest plus the kinetic energy at another state, right? This is technically state 1, before impact, right? We'll call this state 0, okay? This is state 0. State 1 is here, and this is right when the bullet first gets lodged in here, right? So there's a little bit of, there's that initial momentum in here, right? There's V, B, C, right? So to start with, at state 1, do we have kinetic energy, right? Remember, this book uses T for kinetic energy, right? Yes, we have a little bit of kinetic energy from the bullet impacting the block, right? So at state 1, T1 is equal, well, mass A has no kinetic energy, it's not moving. This is going to have 1/2 mb plus mc times v, we called it v prime c squared, right? So we can calculate that. So we can plug in some numbers here. It would be 1/2 of 4.06 times 6.9 squared, which obviously is going to give us 97.87 joules. Of kinetic energy. Is there any potential energy here? No. It's 0, right? Well, I guess it depends on where you put your datum. And there's technically there is potential energy, right? Because if I set my datum to be even with the pendulum, technically I have potential energy from the Minecart, right? But the distance that this moves vertically doesn't change, right? So the total net potential energy between the two states is 0. So we're going to say that the potential energy is actually 0 when in fact there is some here, but we know that it's going to be equal on the next one, so then it would just cancel each other out anyway. Right? So let's move to the next state, right? State 2, what we've called state 2, and that's going to have kinetic energy, right? Now in this case, both the mass of A and the mass BC have the same velocity, which we call VA prime, right? And we solve for that up there. The y direction velocity in this case is 0, right? For the block with the bullet in it, right? Because it's stopped. So we're just not going to talk about it because we don't need it. But it's 0 because at this point, this is a turning point, right? So it's going to be 0 there, but it's still moving horizontally. Okay. So we've got this, right? This makes sense, right? Everybody, we've got the same velocity, right? So we'll plug some stuff in here, right? This will be 1/2 of MA, which is 5 plus 4.06 times 3.1 squared, right? And that's going to give us 43.86 joules. Okay. And then potential energy, right? In this case, we do have potential energy that we need to deal with. And that's going to be mass B plus mass C times gravity times the height that it travels, right? .06 times 9.81 times height. Now I'll put my things together here, right? Because remember this is 0. So I get T1, which is 97.87, is equal to T2, which is 43.86, plus 4.06 times 9.81 times each. So the height, maximum height, has to equal, 1.3 36 meters. Fun times. So what's the what's the takeaway? Right. So this is a system of particles, right? It's a system of particles. These particles move and they're constrained to move with one another. We need to be able to know, right? And this may be conceptually less intensive than the problem with the cars that we did yesterday, right? But same general idea, right? You need to sum the momentum of each of the individual pieces, right? At this part, we start off with, I need to know what, so just break it down into time steps, really, is a good way to think of it, right? Sequentially, what happens? The bullet is shot. Everything's at rest, and then the bullet impacts block C. That's going to cause some horizontal motion. Because why? Because if this string breaks, this is a very uninteresting problem, right? The tension has to be strong enough to hold on to the block, otherwise the whole problem is boring, right? Okay, so this is going to cause an x direction velocity for C, right? This is now driving the entire motion of this system, right? C starts moving to the right, it'll start to swing up, right? This is when we get here. Now this has some initial momentum, right? This is moving this way. The entire system is now moving, and at some point, this pendulum will reach a maximum swing height, at which point its horizontal velocity will be the same as the horizontal velocity of the cart. And this is our final state, because we want to solve for this height. And because we know that height, right? So there's three steps to this problem, right? There's the initial momentum impulse part. Then there's the second momentum impulse to figure out how much momentum do I have after the bullet is in the block to get to this state over here, right? So I need to know, how am I transitioning from this state to here, right? There's some momentum that from the initial impact that's being transferred into the cart, right? Because we need to know how fast the cart's moving, right? How do we figure that out? Well, the total momentum of the system is the sum of the momentum of all the particles, right? Sum of the momentum of all the particles plus the sum of the impulses is equal to the sum of the momentum of the particles at some other time, right? And the third step is using work and energy in the final state with everything that you've done for setup, right? So sum your kinetic energy for each particle, right? And remember, we'll go over one in class too that's a little bit different and uses some angular momentum stuff, right? But energy is energy. Energy is a scalar. You can add energy in any direction. You can add energy of any type, right? You can add angular energy to linear energy if you want, because the units are the same. And it's just a total amount. Whenever we're trying to find energy, we're finding a total amount of energy in a system, especially if we're using conservation of energy, right? Because we're just tracking how much energy is used by different portions of our system, right? Mechanical energy in this class.